Hi, everyone. My name is Andrew Vanderburg, and I'm excited to be able to have this opportunity to talk to you about machine learning and exoplanet detection and vetting. In the last 30 years, we've begun to discover the first planets around stars other than our own sun, mostly using indirect methods. We mostly look for indirect signals in the light from stars to find presence of planets. So that begs the question, for all of these planets which we believe we found, how do we determine whether any given signal is really caused by a planet or is caused by something else going on in the system, something that might mimic the existence of a planet? Early on in the history of the field, this was really not a huge problem. Most of the early planets that were discovered in the first 10 or 15 years of exoplanet discovery were found via the radial velocity method. That is, using spectra to identify periodic Doppler shifts of stars back and forth, indicating the presence of planets. Relatively few stars were searched by radial velocities, on order of 1,000. And of these stars that were searched, there were relatively few false positive scenarios. It's pretty hard to mimic the signal of a star Doppler shifting back and forth, at least for relatively large planets like the ones that were being discovered in the early years of the field. So these surveys had relatively few false positives. But later on in the mid 2000s, when transit surveys began to discover their first planets by looking for the dimming of light periodically around stars, false positives became more of a concern. One reason that planets discovered by transits are more difficult to identify from false positives is that planets are not the only things that can cause stars to dim. There are a variety of phenomena that can cause stars to appear to be less bright, such as eclipsing binary stars that are nearby, blended with the light of the target star. It makes you think that there's a small diminishing of the light. Alternatively, instrumental systematic effects can cause apparent dimmings in brightness that can be difficult to distinguish from real planets. And then finally, down here is an example of a real planet orbiting a star. So for each of the signals detected in transit surveys, you have to ask the question, is this signal due to a false positive, such as an astrophysical object like an eclipsing binary, or is it due to a planet? So another problem that make transit searches more challenging is that they observe many more stars than the radial velocity surveys in the first few years of exoplanet discovery did. Routinely, transit surveys observe 10 to the 5 to 10 to the 7 stars, and that means that there's a lot of data, that's a lot of signals that you have to wade through to find the planets. Early on, the first transit discoveries were made by ground-based telescopes, in particular, really small instruments such as the KELT telescope, the kilodegree extremely little telescope. This is the telescope right here. Really, it's just a fancy camera lens that's attached to a mount, but it was very successful at finding planets. It's found over 20 of them so far. But the problem with these ground-based surveys is that they have relatively high false positive rates. In some cases, more than 95% of the signals that are found in ground-based surveys are false positives. This is a pie chart based on data from Dave Latham, who followed up ground-based transiting planet candidates from a variety of surveys using facilities at the Center for Astrophysics. And he found that about 98% of the candidates that he was sent ended up being false positives. So this makes it really hard to go through by hand and identify all of the possible planets and sort them out from the large number of false positives. In the last decade or so, space-based surveys, and in particular the Kepler mission, have driven massive leaps in our understanding of exoplanets, and they've caused these big jumps in the number of planets that we've known about over time. Space-based surveys like Kepler and TESS have lower false positive rates than ground-based surveys, but they still have very high data volumes and they still have a large number of signals. For example, in Kepler, there are about 100,000 possible signals that could be due to exoplanets that have to be sorted through. And in TESS, that number is exceeded almost every month. And in TESS, we now have something on the order of 2 million signals that you have to look through to determine whether each one of them is a planet or a false positive. So how can we go about sorting through all of these possible planet signals, these huge volumes of data, to identify the signals that are most likely to be real planets and the ones that we can actually have confidence in being real? So there's a couple of options that have been used historically. And the first historical option is that humans should look through each of these signals by eye and determine based on their best judgment whether it could be due to a planet or not. Historically, this is how most planet candidates have been found, at least at the beginning of each individual mission. This is because humans have a couple of advantages. The first thing is that humans are really good at learning how to classify objects with very few examples. So think back to when you were a child and you were first learning about your animals. How many cats did you have to look at before you could recognize what a cat was? Most likely, you didn't have to see very many cats at all before you noticed similar features between all of the cats. This is one of humans' strengths in terms of being able to learn new objects and learn new classifications. We don't need very many examples of a particular class of object to be able to identify more of them in the future with very high accuracy. Another pro of humans is that we're clever and we're capable of generalizing our knowledge to new and unusual situations. So, for example, in this picture here on the left, this cat is dressed up in a dog costume, but we as humans have no problem identifying that this is really a cat and not a dog. And a similar thing can be very beneficial when we're looking at transit signals. Over here is a signal from the planet host star TRAPPIST-1, which looks very unusual. You see these weird dimmings and these weird patterns in the brightness of the star. It takes a human being able to generalize their knowledge about exoplanets and what transits look like to realize that what's happening here is there are actually three planets all going in front of the star at the same time, which is causing this strange and unusual signal. Unfortunately, humans have some downsides as well. And the first thing is that we're relatively slow at making these decisions. These I'm scrolling through right here. This is a PDF document showing all of the information that humans might use to look at determining whether a given signal from the Kepler mission is a real planet or is a false positive. There's 20 pages of information here, and a human can at most go through them about a second per page. And usually the humans will want to take a longer time to very carefully make sure that they understand what they're looking at. This means that if you want to look through something like 100,000 signals, it will take a very long time for a human to do. The other problem with humans is that we're inconsistent. Depending on what kind of mood we're in, we may make a different decision on one day or another. So if you look at this signal here, this is a relatively ambiguous case. Could this be a planet or could it not be? It's very hard to tell from here, and it's kind of a 50-50 coin flip. So depending on what kind of day the humans are having, maybe this is a great day, there's sunshine and rainbows everywhere, you've just won the lottery, you're having one of the best days you ever had. You might say, yes, this is a planet because I'm feeling good and I'm feeling optimistic about life. But on another day, when it's raining outside, maybe you've been stuck in traffic, you might look at this same exact signal and think, no, this can't be a planet. Nothing else is going well in my life, so why would this be a planet as well? This kind of inconsistency makes it really difficult for us to characterize exactly what humans are doing and understand how effectively we can make these measurements. So another option that's recently become more common is using automated tools taking advantage of artificial intelligence to identify planet candidate signals. And when I say artificial intelligence here, I don't necessarily mean the Terminator. I mean a class of algorithms that are designed to mimic the decisions that an intelligent human might make. And that's exactly what we're trying to do here. We're trying to mimic the decision of planet versus not planet that an experienced human vetter would make when they look at a planet candidate signal. Historically, automated tools have taken a longer time to develop, so they only reach maturity after human candidate vetting is well underway. So even though for the first 5 years or so of the Kepler mission, almost all of the planet candidates were identified by hand, eventually tools like the Kepler RoboVetter have been added in and built so that they can do these tasks automatically. And this has led into other tools as well, especially the TESS exoclass, which is based closely on the RoboVetter from Kepler. There are other tools and techniques that have been used from ground-based surveys, such as the SIDRA technique, which is based on random forest classifications and used for surveys such as the Qatar exoplanet survey. And there's a couple of similar systems that are being used for the WASP planet survey and the next generation transit survey. And more recently, there have been more sophisticated machine learning algorithms, such as deep convolutional neural networks that have been used to search data and identify planet candidates and data from Kepler, K2, and TESS. So it takes a little bit longer for these algorithms to come to maturity, but once you do, they have a lot of promise. So as I mentioned earlier, recently, deep learning with neural networks has become a common strategy for this kind of classification task. And this makes sense because these algorithms have actually shown to be very successful in the past decade or so at tasks such as image recognition. So here's an example of what a deep neural network can do. So over here on the left, there's an input image here. This is a dog sleeping in a laundry basket. And what we can do is we can take this image, we can convert the pixel values into numbers and send them into this neural network. Each of these dots here represents a node in the network, and each of these nodes performs mathematical operations on this image that eventually take the information in the image, abstract it, and eventually turn it into just one number, which is the probability or a classification of whether the image is of a cat or a dog. And in this example, the neural network gets the answer correct. And this type of technique, deep learning, has become state of the art recently in fields like computer vision. And it's very impressive what it's able to do. Deep learning can actually tell the difference effectively between two very similar types of dogs, just for an example. Over here on the left is an Alaskan Malamute, and over here on the right is a Siberian Husky. These dogs look pretty similar to the untrained eye, but deep neural networks and computer vision have been able to distinguish these reliably using this kind of technique. So can we use this very powerful tool to figure out whether any given signal from a transiting planet mission like Kepler or TESS is indeed caused by a planet or is caused by something else like a false positive? So if we were able to do this, there would be some big advantages. The first thing is that robotic classifications, these machine learning automated classifications, are always going to be consistent. Machines don't have good days or bad days. They just always classify planets or not planets with a robotic indifference. The other really important benefit is that these systems are very fast. This is a movie that was made by a former student of mine, Anne Dattilo, who's now a grad student at the University of California, Santa Cruz. She's showing how you can classify about 30 signals or 3,000 signals in about 20 seconds on her laptop. This would have taken me about 3 hours to do if I were doing it by hand, and she can do it with probably better accuracy than I could. There are, of course, downsides to these automated systems as well. Deep neural networks and automated systems can be tricked more easily than humans. Even though a human might realize this is a cat wearing a dog costume, it could trick the neural network, especially if it's never seen anything like this before. These neural networks are not nearly as able to generalize and not nearly as able to take leaps of logic that humans are able to do. So to summarize the pros and cons of each of these two approaches, humans are better at new and unusual circumstances, and we're less likely to make easy mistakes. But on the other hand, neural networks are faster and they're more consistent. And in the big data world, as we start finding more and more possible planets and need to classify them, machine learning will eventually win out. And that's what I wanted to talk about in this talk here. So I'm now going to go through an overview of AstroNet, which is one of the prototype neural networks that's been used for Exoplanet development. I worked on this project with Chris Chalou, who at the time was a Google software engineer working on machine learning research at Google Brain. Now he's actually moved into the astronomy field and is a graduate student in astronomy at the Center for Astrophysics. AstroNet is a neural network designed to identify planets and separate them out from false positives in Kepler data. Basically, what we do is we take the light curves, we fold them on their periods, and we take averages of those bins in phase. That converts these light curves, which are time series of something like 60,000 points, into a one-dimensional image of a consistent size. And image recognition is exactly what these convolutional neural networks are very able to do well. So what we can do is we can send these one-dimensional images into the convolutional neural network. Each of these two images, one is zoomed out over the entire orbit of the planet, and one is zoomed in on the most important part, the transit. We can send them up through individual convolutional neural network columns where we perform similar operations on each of these points in the image. We convolve different filters across them, and we see what those filters respond to in this one-dimensional image, this one-dimensional time series image. And we can then train their neural network by adjusting the operations in these that are represented here by these circles to eventually decide whether or not this is a planet or a false positive. This is what the architecture actually looks like. This cartoon example here is a simplified version. You can see here that we have the two inputs, and there's many more layers of this neural network. That gives it more power to make subtle distinctions and gives it more capability to accurately determine whether or not a given signal is a planet or a false positive. In this case, you can see that this signal has this characteristic bowing shape out of transit. So we would teach the neural network based on other examples that this is not a characteristic of a planet. These bowed out of transit shapes are characteristic of stars. And hopefully this neural network would then recognize that a similar signal to this is not a planet. When we trained this on data from the Kepler mission and tested on a held out test set, signals that the neural network had never seen before during its training, we found that we were able to make these classifications with about 96% accuracy, which is a pretty good start. Since then, we've been working on adapting the neural network to data from the K2 mission. This is a work that's been done by Anne Dattilo, who I mentioned is now a UC Santa Cruz grad student. She was able to make a proof of concept neural network for K2 using a very similar method to our original AstroNet for Kepler. And she used this to discover two new planets in data that had previously not been vetted. There were about 30,000 signals that had never been looked at by humans just because there were too many of them to go through. She was able to classify these very quickly using her algorithm and find these two new planets that were previously unknown. And finally, we've been working on adapting this strategy to the TESS mission. This is work that was originally led by Liang Yu, who was an MIT graduate student at the time and who's now moved on to working at Audi in Germany. And now we're working with Dan Moldovan, who is another software engineer from Google, and a team including Chelsea Wong, Michelle Kunimoto, Avi Sporer, and Evan Tay at MIT right now. And we're using the expertise from Dan and from the machine learning side and our expertise from the TESS mission with understanding the signals and being able to classify them and build training sets to try to adapt this neural network for use in tests. We've been able to include additional diagnostic information, such as additional views of the light curve. Instead of just showing one view of the entire light curve, as we did in Kepler, and one zoomed in view of the transit, we can give additional close-up views of different important parts of the light curve that help us improve the performance of the neural network. Our AstroNet neural network triage is now currently being used to reduce the human workload in vetting planet candidates from the MIT Quick Look Pipeline. It's being run every sector as the test data come down, and it's significantly cut down on the amount of time that humans have to look at each individual signal. Neural networks for planet detection is a really active field right now, and there's tons of other papers and tons of other techniques that are being used and developed to try to make these processes more effective. And it's really exciting to see all of the work that's being done in this field. And we expect that as we continue to make more progress on developing these algorithms, we'll be able to use them and find more planets and build more consistent catalogs of planet candidates. So I'm going to put up my summaries here, which are that in the big data era, automatic tools for inspecting data are only going to grow in importance. And deep learning in detecting exoplanet candidates, especially in Kepler, K2, and TESS light curves, is one of the applications where this is going to be really important. We're already making great progress, and we're already using this in real life to vet and identify planet candidates and reduce the workload for humans. So as these techniques develop and continue to improve, we should be able to find more and more planets, build more and more accurate planet candidate lists, and unlock a lot of additional science that wouldn't be possible without this new technique. And thank you for listening.